Yeah, hello friends. Continuing, we have got now a very important topic that's called a Zener Diode, and many questions come in the competitive exam from this Zener Diode. In fact, the only numericals, most of the numericals, in fact, from the diode side are from this Zener only, isn't it? So we'll discuss a bit more in detail. So here I have for understanding the Zener Diode in somewhat a bit more comprehensive manner. So here I have drawn the unbiased p-n junction, the energy bands, as you know. So lots and lots of electrons onto the conduction band of this n side, and less electrons on the conduction band of the p side. And we know that the diffusion happens. Diffusion happens for what? Diffusion happens for the electrons from the n side, where because in n side there are lots and lots of electrons to the p side, to the low concentration. Okay. So we know that the only few electrons are able to diffuse into the in the unbiased condition, and whatever electrons are diffusing into the unbiased condition are again, you can say, sent back. Equally number are sent back by this electric field. So that is what is the unbiased condition. Now if you remember what happens in the forward bias, in this forward bias, this barrier potential difference, or this energy barrier, is decreased because of the reasons we have already discussed. So let's compare side by side here. Let me just shift it a bit. Okay. So so these levels are same, but as you can see now, instead of having this large level here, yeah, this large level here, this level, instead of this level we are dropping it to this level, and so the energy height is the barrier height is less, and so lots and lots of electrons are able to diffuse into this in the case of forward bias condition. Same thing can be told about the holes also. These holes initially they were not able to diffuse onto this side. All they are having high concentration here and low concentration here, but because of this forward bias condition, because of the decrease in the overall level in the of energies in the p side, these holes now will be able to diffuse onto the n side, thereby giving rise to this diffusion current. So electrons here and holes here, lots and lots of diffusion current that we have already discussed. So again, now coming to the reverse bias condition. So instead of this barrier height decreasing, we know that in the reverse bias the barrier height is increased. So if we compare this thing here, so this is unbiased condition on the left side, unbiased on the left side. So there's the energy gap, and then the bigger energy gap here on the reverse bias. And so these electrons, they can't diffuse it. Why? Because this is the energy gap, and there is no quantum state in this energy gap. So this electron, while diffusing here, they can't go into this no man's land here, isn't it? So electrons can't diffuse here. So that is what is reverse bias condition. Now what happens in extremely high reverse biased? So that is what is shown here. So what happens in extremely high bias? Let's compare side by side with the reverse bias condition. Alright, so on this okay, it can't come in the entire frame. So anyway, you have discussed, you have seen the reverse bias thing. So let's discuss this extreme high reverse bias condition. Okay, so what happens here? Because of the extremely large reverse bias, this gap increases so much, so that these energy levels have increased, and now the energy levels of the valence electrons on p side have come at par, almost same as the energy levels of the electrons in the conduction side. So what happens is some kind of a quantum tunneling effect. What is a quantum tunneling effect? These electrons of the valence shell of the valence in the valence band on the p side, because of this extremely strong electric field which applies a tremendous amount of force on them, this electric field directly makes them go from the valence band of p side to the conduction band of n side. Now exactly how it happens and why it happens, for that we need to understand quantum mechanics. Definitely it is not within the scope of our studies. Even I was going through the video lecture of basic electronics course uh, given by Professor Kalmakar in IIT Madras, and there also, while explaining this Zener diode functions, he said that this quantum tunneling phenomena is beyond the scope. But anyways, so let's just assume that the electrons in the valence band of the p side will be able to go very easily to the conduction band of the n side. So what we can say is that lots and lots of electrons will be available now. Anyways, see, the point is that on the p side, electrons are mostly onto the valence band. So lots and lots of electrons are there in this valence band of p side, and all of these electrons now are available to go into this n side. Thereby they can conduct electricity. So this will give rise to a very high reverse current. Okay, so let's just take a paper here, and let's draw the p-n junction in the reverse bias condition. So here it is. Pn. So reverse bias condition in this, and very high reverse bias. So see, why there was less current in the normal reverse bias condition is because the number of electrons that were available here were very small, isn't it? How the electrons are supposed to go? See, the current from the battery should be like this, isn't it? Coming out from the positive terminal. So this is the direction of current here, like this, which means that the electrons are supposed to go like this. They are supposed to go like this, and then they are supposed to go like this here, electrons. But how many electrons are really available to go from p side to n side? See, initially we discussed that these electrons are very less in number. Why? Because in p side they are minority in number. So very less, few electrons onto the p side, so they can't drift onto the n side very much, and that was giving rise to a very low this reverse current. I mean, the electrons movement is like this, clockwise, and the reverse current is anti-clockwise. So that's why this current is here very low, because of less. But as we keep on increasing the EMF of this battery here, isn't it, what happens is that, as we discussed, the electrons in the valence band of this p side, now these are readily available to go into the conduction band of n side. So thousands and thousands of electrons into the conduction band that were earlier not able to move, now this will all be going into these regions, and thousands of charges have suddenly come up, and they are ready to conduct the electricity. So what happens is that suddenly there is a huge surge in current in this reverse mode, and we draw that the circuit something like this. So this reverse bias region in the reverse voltage, and suddenly when we keep on increasing the EMF of the battery, that means the reverse potential difference, the current again surges to a very large value. Obviously we are showing the negative current because it is not flowing from the electrons are not going from n to p, but the electrons are going from actually p to n. So as you know, why we show the negative value of current in the reverse bias. Just a terminology, isn't it? So very high. So this is called the Zener breakdown. Zener breakdown, and it happens exactly at a very sharp voltage, which is called the breakdown voltage. So this is breakdown voltage, isn't it? Now this breakdown voltage depends on several factors like the doping concentration, even the temperature, and many other things. Okay, so moving ahead now. Yeah. So moving on to these slides here. If you want, you can write all this nonsense. Okay. Now one thing which is very important is that to get a very high value of current, or to get any value of current, by the way, the voltage across the Zener remains almost same. Almost same means 99.99% same only, isn't it? And so we can have any amount of current, and the voltage across it, the voltage across the diode doesn't change. And since the voltage across the diode doesn't change much, negligible change, we can use it in as a voltage regulator. So how does the voltage regulator circuit looks like? Let's see. Okay, so the same things are written, you can just go through it. Okay, so the circuit symbol for the Zener diode is this. So a typical diode like this, just like this, except that we do some kind of a Z kind of thing, isn't it? Does this look like a ZZ? How about if we draw it like this? Now it is Z, Z. Anyway, so Zener, so that's the circuit symbol for the Zener diode. Anyway, moving on. So this is how the circuit should look like, isn't it? So we want a constant potential difference across a load resistance, connect it with a Zener. Why? Because across the Zener diode, although no matter what current flows, voltage across it remains same. So whatever is connected in parallel with it, the voltage across it will also remain same, isn't it? Well, not that simple. See, what is the problem in this circuit? Let's say the load resistance is such that we need a constant potential difference of 20 volt across this one, and so the voltage of this thing the breakdown voltage of this should also be 20, isn't it? Because 20 will be maintained here, 20 will be maintained here. But what is the EMF of the battery? EMF of the battery is 30 volt, let's say. So but the voltage drop across this is how much? It's 20 volt. So where will the remaining 10 volt potential drop? Across AB? Yeah, maybe, but this AB resistance is very less because this is like a copper wire, isn't it? So what we do is we put a shunt resistance. What is the shunt resistance? The shunt resistance will dissipate the remaining amount of the potential difference, and it will control the current. Otherwise the current through this wire and through the Zener will become very large. For example, let's say if we go from here to here, what is the potential drop as we go from, let's say, this point C to point D? Well, the potential drop is 20. So from here to here, potential change is minus 20, and then minus 20 plus 30, isn't it? So minus 20 plus 30 means plus 10. So overall there is a potential difference, and if there is a potential difference between these 2 points A and B, what happens if there is a zero resistance here? Potential difference, zero resistance, infinite current tends to infinity, everything will burn, your Zener diode is gone before you can use it. So what we do? Put a shunt resistance. So the shunt resistance is used to control the current here. Alright. Okay. Now this Zener diode comes in a variety of range. Some of the Zener diodes have the breakdown voltage of 3 volts, some 5 volt, and even 50, 100 Zener breakdown voltage. So it all depends on the fabrication of the Zener diode, how it is made, isn't it? So we can adjust the breakdown voltage by our own will. So we need to tweak certain things. So moving on now. Now let's discuss the problems with the shunt resistances. So first we'll discuss the problem with very high shunt resistance. Now let's say there is a shunt resistance here, there is a load resistance. The load resistance is 100 ohm. Consider this particular situation example. Now we want this load resistance to have a constant potential difference of 20 volt, and so we want to connect it to a Zener diode that will work in the reverse way, and that will dissipate and that will have a constant potential difference of 20 volt across it, no matter how much current flows, isn't it? That this thing. So this is how much? 20 volt. So whatever current, the voltage is always 20. So 20 volt. So 20 volt here also. Now, so we want voltage across this to be 20, but let's say our input voltage, which is a varying voltage, is varying between 30 volt to 40 volt. So what happens? Let's say we forget about the Zener right now, and we have the load resistance of 100, and 400 ohm is the shunt resistance used. Alright, so what will happen in absence of Zener? Well, there is a battery, two resistances, equivalent resistances, sum of these two, 500. What is the current? The voltage EMF 40 divided by the total resistance, so it is 2 by 25. So what is the voltage across the load? That is equal to the current, this multiplied by what? The resistance. So it comes out to be 8 volt, which means out of 40 volt, 32 is dissipated across it, and only 8 volt is connected. So 8 volt potential drop. So when we connect this resistance, which has a 8 volt of potential drop across it, to a Zener diode, Will this diode even achieve the breakdown? No. Why? Because the Zener will achieve the breakdown only when you reverse bias it with a sufficient 20 volt. But how much voltage you are applying across this? Only 8. So how will it break down? So what will happen? Current will flow just like that. This will be reverse bias but not sufficiently reverse bias to break down it. Voltage across it will remain 8 and remaining 32. Why such a high voltage is dropped across this? Because we have used tremendously high RS, shunt resistance. So let's decrease this value, isn't it? Alright. So here is another one. The same example. But what if we use 60 ohm now? So let's forget about the Zener diode right now. This is 60 and this is 100. So what is the equivalent? Equivalent is 100 plus 60, 160, and then the current, as you can see on the EMF, 40 and 40 by 160, 1 by 4, isn't it? So V across the 100 is 25. So how much voltage will drop across is 25. So 25 here, and how much is left? 15 is left, isn't it? So 40 is divided into 25 and 15. So voltage. Now that you can say that the voltage across the resistor is greater than the Zener breakdown region, isn't it? And now when you connect this resistance to a Zener diode, immediately you can see that the voltage across the Zener will become this 25, and as soon as the voltage across the Zener diode becomes 25, what will happen? It will break down. Okay. Then what? What happens after the Zener diode breaks down? As soon as it breaks down, the voltage across it becomes fixed. Okay, so let's see the circuit here. So let's say we apply the Zener diode here. Yeah. So we have applied Zener diode. Voltage across it will become how much? 20 volt. So this 25 is gone now, 20 is there, and this is a 100 ohm resistance, and this is a 20 volt across it. That is what Zener will maintain, because the Zener has broken down. So how much current will flow through it? How much current will flow through it is, see, 20 volt, 100 ohm. How much is the current? V by R. So it is 0.2 ampere, isn't it? But if this is 20, because it has dropped from 25 to 20, it should increase from 15 to 20, because overall what is the battery EMF? 40. So if 20 is dropped here, then remaining 20 should come. So instead of 15, this will become how much? 20. Now if this becomes 20, how much is the potential drop across it? 20. So what is the current? It is 20 by 60. So it is around 0.33. Am I right? 0.3. Yeah. So this current will become 0.33 ampere. This will become 0.2 ampere. And how much will go through the Zener diode is 0.13 ampere. And so it is functioning properly. Bingo. So we are able to utilize the Zener. See, if Zener was not applied, what would have happened if this was 40? If Zener was not applied, this would have been remaining 25, isn't it? So because so instead of 25, we have made it 20 by connecting the Zener diode in parallel. So we can say that this current is increased, isn't it? Why? And because this voltage is increased. Why? Because earlier without connecting the Zener, this was how much? 25, and this was 15. Now this has decreased from 25 to 20. This should increase from 15 to 20. Since the voltage across this has increased, the current has increased. Who will absorb this more current? The Zener diode. So some current will be bypassing through it. Alright. Okay. So I hope you are understanding the difference here. Difference between the two circuits. The two circuits being the one before using the Zener and the one after using the Zener. Before using the Zener, the current was 0.25 ampere, 1 by 4. This one. So 0.25 was passing, 0.25 was passing. But as soon as you connect a Zener diode, what happens? This 0.25 drops down to, so let me draw it in the separate circuit. This 0.25 drops down to 0.2 ampere. So this becomes 0.2, but this is increased, isn't it? How much this has become? 0.33. So this one increases, this one decreases. The remaining will bypass through the Zener diode. So that is what is written over here. So let's move on. So this is exactly what is shown. I made a mistake actually. 1 by 3 is not 0.66. So just ignore my stupidity here. 0.33. So 0.33 means so 0.13. Alrighty. But there is a problem with 60 ohm also. What is the problem? The problem is that, as I said in the previous case, before the starting of the problem, that the voltage is fluctuating continuously from 30 volt to 40 volt. So this is varying continuously from 30 volt to 40 volt. So with the 40 volt it is fine, but what if there is a 30 volt? Will the voltage across this become greater than the Zener voltage in absence of Zener? So forget about the Zener diode right now. This is 60, this is 100. What is the total resistance? 160. How much is current? 30 by 160. 30 by 160. So what is the voltage across this? I into R. So I is this. This is the current here, and resistance is 100. It comes out to be 18.75. So as soon as this fluctuating voltage is dropped from 40 volt to 30 volt, because I said in the beginning that this voltage, input voltage, varies continuously between 30 volt to 40 volt, and we want a constant voltage difference of 20 volt here. So what if this becomes 30? This becomes only 18.75. So as soon as this voltage is decreasing, this becomes again the Zener will not achieve the breakdown region, isn't it? Because the voltage across this will only become 18.75. So what we need is, even the smallest value of this input voltage should be able to make this resistance have so much potential drop that this is breaking down the Zener voltage. That means in absence of Zener diode, the voltage across RL should be greater than V Zener with the minimum input voltage. So that is what I have written. So let's check what is the maximum value of the shunt resistance we can use. So let's say we have a circuit in which there is a varying voltage, and the voltage varies from Vmin to Vmax, and this is how the thing is. And the current in absence of the Zener diode will be the minimum current in case of V minimum, isn't it? Because in maximum case anyway, we'll be able to achieve the breakdown if we can achieve the breakdown in V minimum case. So what is the current? Current will be equal to this V minimum divided by the series combination of these two resistances. So what is the voltage across this RL? This voltage across this RL is IRL. This is I. So just multiply this I with RL. And what we want is that in absence of Zener diode, this is having a voltage greater than V Zener, so that it can break down the Zener voltage. So we want this to be greater than this. Just a simple inequality, transferring this here and this here, and transferring this here, so we get this. So RS should always be, so this is, we can say, the upper limit of RS. So for example, in our case, see, V minimum is 30, because this is going from 30 to 40 volt. The Zener voltage is 20 and the load resistance is 100. So if we plug in these values, what we get is that the shunt resistance should be less than 50 ohm. So you see the problem with the 60 ohm. The 60 ohm was able to make the Zener breakdown with 40 volt of input voltage, but that 60 ohm was unable to break down the Zener diode with a 30 volt of V minimum. So we got this. So this is an important formula, isn't it? Now moving ahead. Okay. Now that we know we will be using this shunt resistance which is less than 50 ohm. What if we decrease the values of this resistances more and more? There is a big problem. Just like there is an upper limit on the value of the shunt resistance, there is a lower limit also on the value of the shunt resistance. So let's check what it is. Okay. So you see here, let's have this 30 volt. So we know that when this is 30 volt, So the voltage across this will be, in case of breakdown, 20 volt. So 30 out of 30, 20 will appear here and 10 will appear here. And if the 10 is appearing here, how much current is flowing like this? Well, it depends on resistance. For example, if we apply a 40 ohm resistance, so voltage is 10 and the resistance is 40, we get to 0.25. Yeah. So what is the current through RS? I through RS. I through RS is the voltage across it, 10 volt divided by the resistance. So here are some of the values. You can see, just divide the 10 by RS to get the current. And this is the current here. Now out of this current, 0.2 will go here. Why only 0.2? Because this is a potential drop of 20 volt, so this is also 20 volt. So current will be 20 volt divided by 100 ohm, which will give us 0.2 ampere. So out of this I coming through the shunt resistance, 0.2 will go here and remaining will go through the Zener. So the current through the Zener is the total current through the shunt resistance I minus this 0.2. So as we keep on decreasing this resistance, shunt resistance, this current increases and the current through the Zener increases. Now when the current through the Zener increases to a very large value, the Zener diode is gone. It becomes highly superheated. So let's check what is the power consumed by the Zener diode. Power consumed by the Zener diode is given by the Zener voltage multiplied by the Zener current. And each Zener diode comes with a rated power. So the power dissipated, which is Vz into Iz, should always be less than the P max rated. If it exceeds, the power dissipated exceeds the rated maximum power, then that will be destroyed. So here comes a very important point, extremely important. You see here, even the highest value of the input voltage shouldn't flow such a high current through Zener so that P becomes greater than P rated. So for example, let's say we have got a Zener breakdown voltage 20 and it is given that the P rated is 16. So what is the maximum current through the Zener? We know that P rated at max can be equal to how much? Vz Iz. So we get the upper value of Z. So what is the upper value of that? So this 16 divided by this Zener voltage 20, which is 0.8. So maximum current is 0.8. Now when will the current be highest? When this voltage is not 30, when the voltage is 40. Because 40 is the upper limit, so higher is the voltage applied, higher is the current. So we should always use this higher voltage of 40. So 40 is here, 20 is here, so 40 will be dropping here because 20 here dropped, 40 is total, 20 will be remaining here. So this is 20 volt. And how much current we want? Maximum through it, 0.8. So 0.8 and 0.2, how much it becomes? 1. So 1 ampere can maximum flow through it, and this is 20 volt. And so the shunt resistance will be how much? See, let's say the shunt resistance is Rs. What is the voltage across is 20. So what is the current? Current is equal to V by R, and this is 20 divided by the shunt resistance Rs. We know that this shunt current, this should be less than 1 ampere. That means Rs should be greater than 20, solving the inequality. So we came to know that there is a lower limit of 20 ohm here, and if you remember, we discussed also that the shunt resistance should be less than 50 ohm. So less than 50 ohm, so that the Zener works in the breakdown region, and greater than 20 ohm, so that the Zener is still there, isn't it? I mean, not damaged. Yeah. So here comes the two final points. While finding the lower limit of Rs for Zener safety, you should take this input voltage to be the maximum, so that even the maximum current is not such a high value of current. And then finding the upper limit of Rs for proper breakdown of Zener, we should take the input voltage of V minimum. That means even the minimum input voltage is sufficiently able to break down this Zener, and so for that shunt resistance should be very significantly low, because we know that in series combination more voltage is dropped across the higher resistance. So just decrease this resistance so that this voltage drop is high, and some goes here also, isn't it? So that it can break down and then you can get some kind of a Zener effect. So this is just an example. You can just pause the video and do the question. I have done it for you, and this is a typical question that may be asked in your mains exam. So moving ahead now. All right. Okay. Now come to photodiode. Now, diode under reverse bias condition, reverse saturation current flows like this, isn't it? Now this current is very less, and the net current is only the drift current, as you know very well, and the diffusion current tends to 0. Today also we discuss about this barrier height nonsense, isn't it? Okay. Yeah. So moving on. So this is the reverse current. So reverse current is like this. See, this is the electric field of the battery here, and this is the electric field in the depletion region, both because of the battery and also because of the space charges, isn't it? All the positive on this n side, negative on this p side, and this is the electric field. So force on electrons is like this. So electrons go from here to here, and the circuit is complete like this. Electrons like this, and so the current is opposite direction. But as we discussed that the electrons are very less in number, so not many electrons can go from p side to n side. What can be the way of increasing this reverse current? We don't want to break it down. One way of increasing this current is to produce lots and lots of electrons here. Now, how can we produce lots and lots of conduction electrons in p region, whereas in p region only holes are there, whereas the number of electrons, conduction electrons, are very less? Same thing explained about the hole current also in the forward direction. You know what? Okay. One way of generating lots of electron hole pairs so that these electrons can conduct electricity is by shining light. So you know that there is a band gap here. So what happens? This is the EV level and this is the EC level, and for the electron to go from the valence band to this conduction band, what they require? Energy. How much energy? Energy gap. So if we can somehow throw lots and lots of photons, that means we can throw some light, what will happen? As soon as this light is incident on the electrons will be absorbing that photon. As soon as the electron absorbs that photon, and if this photon energy is greater than the energy gap, what will happen? Electrons are absorbing energy, they have got this energy Eg, so they can go into those conduction band. So all these electrons on p side which are fixed here, which are not able to move, which are in their valence band, after absorbing energy, then they can go into conduction band. And when these electrons come into this conduction band, now these are free to move, and so these electrons will jump here. Lots and lots of electrons here will go like this clockwise, and we will get a good amount of current. So what is this photodiode? Photodiode is an instrument which is used to detect whether there are some light signals or not in some kind of a let's say a dark room. So we know that let's say we have a PN junction which is reverse biased, and before this light is shined, there is a very small current. Now put a galvanometer here. I think I have another circuit here. Now, or we can work with that old thing only. So put a galvanometer here, and we know that before shining light the current was